So we're going to start by looking at question 16C here. So last time we did look at B already. So let's see what is happening in 16C. So let's get the problem. Okay, so if you compared this question to 16A or B, you notice that everything really is quite similar. The approach is the same and so on. But the only difference that made me find this question interesting is that in A and B, the interval is presented in terms of time. You can see 0 less than or equal to t less or equals to root 8. Here you have 0 less or equal to t less or equal to pi. And then in C here, what does this mean? And that was the first question I asked myself when I first encountered this problem. And I thought you guys would find that interesting. So I thought of sharing it with you guys as well. So how do you approach it? So the first part is really similar um, to to what we did previously on how you actually get the arc length. So this is an arc length problem. Let's just ensure that that's the case. So yes, here we're finding the arc length of the indicated portion of the curve. And the formula for arc length, as we earlier pointed out, is given by that expression. So we are still using the same formula. So even without understanding how you're going to sort out this, the first thing that you want to do is you know how you get arc length of a curve when you're given an interval. So start from there. So to get the arc length here, we know to say the arc length S will be equal to the integral on the interval indicated, and then you need the magnitude of the derivative of the position function. So this is what you want. And then of course with respect to t. Now the only thing here is step 1, differentiate the position. So the first thing we're going to do is differentiate the position function. And for the position function, we have this expression here. Okay, so if you can't see the screen, try leaving the meeting and coming back. I've got 3 devices on and I'm able to see the screen on all 3. So it means that it should be okay on my end. Okay. So from here, first thing, as you can see, R prime. So you want to differentiate the position function. So when we differentiate this expression, what do we get? So here, R prime, a function of t, will be equal to, when you differentiate this part here, the derivative of 1, that is 0, the derivative of 2t, that will just be 2. So when you differentiate this part, you get 2. Don't forget the unit vector. This is still there. That is still there. So I. Then plus, now we differentiate this part here. So when you differentiate 1, that is 0. When you differentiate 3t, the answer will be 3. Of course, we're differentiating with respect to t. So t is the variable. So here you get 3j. And then next up, you differentiate this part. Derivative of 6, that is 0. Derivative of negative 6t, that will be minus 6. And the unit vector is k. So presentation is kind of important here. Some students would end up leaving out the unit vector at this stage, and I think that fails in terms of presentation. After getting the magnitude of the position vector, the next thing that, not the magnitude, the derivative of the position vector, the next step is to obtain the magnitude of that derivative. The magnitude, of course, is the square root. Of course, this is going to come out by Pythagoras. Now, this is where the unit vectors disappear from the expression. So just get 2 squared plus 3 squared plus negative 6 squared. 2 squared, that is 4. Then we have 9 here. Then we have 36 here. So 36 and 4, 40. So you have root 49. Root 49 is 7. So you have seen that the magnitude of the derivative here reduces to just root 7. Now we go back to our expression for arc length. The arc length is the integral over that interval of this magnitude with respect to t. So where we have that magnitude, we can put what the magnitude is. The magnitude reduced to just 7. So I can put 7 there. When we integrate here, we see that our expression reduces to just 7t. And then this is from A to B. So the only question is, what is A? What is B? So this is where the trick comes in. This is where this part comes in. In most problems, they will tell you what t is and how it is changing, the smallest value of t and the maximum value of t. But in this case, they haven't given us the smallest or the maximum value of t. Instead, they've given us this. It looks weird, but if you just try to pay attention, you'll notice what that actually represents. You see, the only thing so far we have seen that can be presented in this form are coordinates. So these must be coordinates. So it's like they are specifying the starting position and the final position. They're saying our starting position is at -1, -2, 12. And our final position is at 1, 1, 6. Remember that RT expression, this expression is a vector that is telling us the position of this particle. So the points being given here, it's the starting position on the curve, and this is the final position on the curve. So that is the first thing that you have to understand. Other than that, you see the position vector can actually be represented in terms of its parameters, or we can get the parametric expressions from here. This curve can be represented in parametric form, where we can say that this part here represents the position in the x-axis. This part here represents the position in the y-axis. And this part here represents the position of this particle in the z-axis. So by this logic, we see that the position in the x can be represented by this parametric form or parametric equation. The position in the y-axis is represented by 1 plus 3t, while the position in the z is represented by 6 minus 60. You see, all we need for us to finish our expression here, we want to just know at the starting point what was the value of t, and at the final point what was the value of t. The problem currently is giving us the position itself, where we're starting from. We're starting from that point, we're ending at that point. But we are interested in knowing the starting value of t and the final value of t. So how do we understand that? Well, we have just seen that this expression or the position vector can be reduced to these parametric expressions. And in our starting case, where are we starting from? The starting position or the starting point, we are starting from -1, -2, 12. So at the starting point, what was the value of t? So here we not say coordinates are given in terms of x, y, and z. And remember, this is giving us the position on the x-axis. So on the x-axis, when the position was -1, what was the value of t? So I can just put -1 where we have x and try to find what t is at that point. So when you solve this, we'll have -1 minus 1 is equals to 2t. We get -2 is equals to 2t. And finally, we see that t is equals to -1. So t here has come out as -1. Now, you can try this. You see, it's the same point, it's the same position. The only difference is you're looking at it from the x, you look at it from the y, you look at it from the z. You can even try to find what the value of t would be if you viewed this from the y. If you did that, Here's how it would look like. The value of y at that point, it's -2. And then -2 will be here. The 1 comes to the left, becomes negative as well. This is now -3 is equals to 3t. And guess what? We still end up with t is equals to -1. The same value we got there. Why does this make sense? It is the same point. If this is the coordinate axis and this is our point here, the value of t at this point would be the same. The value of x might be different. Let me not do it like this. The value of x might be different. The value of y might be different. And the value of z might also be different. But for this point, since it's the same point on our curve, the value of t would be the same, whether you view it from x, y, or z. So this is why here we're getting the same t, here we're getting the same t. Even if we tried to do it for z, the value of t that would come out would be the same. So there we have it. Our starting point, at our starting point, t is -1. So we have -1 here. How about at our final point? What is the value of t? The endpoint has coordinates 1, 1, 6. So now there's no need for us to do for all 3 points or for 2 points. So just pick one. We know to say it would still be the same. So we can just pick the position vector for x. Since we know at the endpoint, x will have 1, value 1 there. So what would be the value of t at the final position? Since x will be 1, when you solve this, you have 1 minus 1. You have 0 is equals to 2t. 2 cannot be 0, meaning t has to be 0. So our final point here is at t is equals to 0. So there we have it. Our final position, our final point, it's at t is equals to 0. So we can put 0 there. So we now have our interval correct in terms of t. So we can now finish the integration here. So first upper limit minus the same thing, but now lower limit. We see that the final answer will be 7, whatever the units are. So that becomes the expression for the arc length.